call it the centroid. So different names for the same topic. Again, what you want to think about is you're trying to, if this was flat, so I have the shape here, you're trying to find out one point where you could balance it on the tip of a pencil. And we had formulas, so last class we developed these formulas, is how do we find x bar? It's sum of the moments about x equals 0 divided by what? The total weight or the sum of weights. What I want you to imagine is that I've got this three-dimensional shape and it's heavy. Its density is 15 pounds per foot. And we calculate the centroid. And then I take that same shape and cut it out of styrofoam. And styrofoam's density is 1 pound per square foot. How does the centroid change? So I found the balancing point for the heavy one. Would the balancing point even change for the light one? You agree it wouldn't? It's just the shape that matters. So I can assume that the density of this is always 1 pound per square foot. So if I had something, so this is that's 3 foot by 2 foot. If it was 6 square feet and the density was 1 pound per square foot, how much would this weigh? 6 pounds. So by adjusting the density to 1 is numerically the weight and the area are exactly the same. We've got different units, but the number in the denominator here would be the same. So all we need to worry about is area. So every time I say weight, I'm going to replace it with the proxy of area. So, and just so we're clear about two things. A moment is going to be, quick review about moments. A moment measures the tendency of something to cause the system to tilt in that direction. And we decided that tendency depends on how much weight you have here and the distance it is from the balancing point. So what's the moment for this? It's 15 foot-pounds. In general, the moment is going to be the distance times the weight. I'm doing the calculations here. It's a distance times the weight. And then finally, my y-bar calculation. We'll call it total area. So my y-bar calculation, so you get the sum of the moments about y equals 0, and I'm dividing that by the total area. So I think it's easiest to see how these work. As we work through a few examples. Remind me, we have not done any examples yet, is that true? Have we done this example yet? What's like? We did? Oh, yeah, we did. Yeah?
Oh, yeah, we did.
Okay, cool. We got another one. What about y equals x squared from 2 to 4? Okay. So we've done that one already. And I've got a second one for you. So here's my shape. And we're just going to go through the same process we went here. There's one slightly tricky thing in one of the calculations. Did y'all notice we are being recorded again? We have a much better system. So there's some technical details about trying to get it up on YouTube. It should be up shortly. Do that as soon as I can. Technically, it's up. So everybody's good with all the lectures being recorded, and you're not going to quit coming to class? Well, I just actually saw a study this morning. They did a meta study of all the different studies of what predicts student success. And do you know what the number one predictor is? Attendance, absolutely right. So more than anything else, it's attendance is the best predictor. That's how well you're going to do in school. Come to class. So let's do x bar first. And x bar is a fraction. Get this pen to last as long as I can. What is the numerator of this fraction? It's a sum of something. It's terrible. Sum of what? Sum of the moments about x equals 0. And what's the denominator here? Yeah. Again, technically it's the total weight, but we adjusted the density to 1, so the weight is equal to the area. And areas of shapes like this are exactly what integrals were invented to do, or at least the first thing. This is how we introduced integrals in Calc 1, is how do you find the area of the shape like this? And that's just the integral of the function from 0 to 2. And I'm thinking about the top now. So I want to do the moment about x equals 0. And is x equals 0 a horizontal or vertical line? Very good. Agreed? And how do I calculate a moment? It's the distance. And technically, it's a distance times a mass. And instead of mass, what am I going to write here? Area. So once again, we adjusted the density to 1, so the area is the weight. So I'm trying to make a slice out of the original region so that all the points in that slice have the same distance from x equals 0. Would I use a horizontal or a vertical slice? Again, I want all the points to have the same distance from x equals 0. So it would have to look like this. So for that first calculation, the distance from x equals 0 it's that horizontal distance. What letter measures horizontal distances? X. And specifically, x is the distance, the horizontal distance from the y-axis. So this is exactly x. And then for the area, I need to do base times the height. Is this base a dx or a dy? It's a dx. So that's a little slice out of the x-axis. And for this vertical distance, for the height that's a vertical, the top is given by y equals x squared, and the bottom, you don't need it for this one, it's a good habit to get into, is given by y equals 0. So what's the height of this rectangle? X squared. So for the area calculation, it's going to be x squared times dx. So this is the moment for one slice. And then for x bar, we need to do the sum of all these moments. So we're going to add these up from 0 to 2 of x times x squared dx. Y bar next. And one thing you want to be careful of, x equals 0, algebra students refer to that as the y-axis. And your book makes an abbreviation. Well, the sum of the moments about x equals 0 is just, that's the net effect of the moment about x equals 0. And your book, just to make it confusing, calls this m sub y. So why is the book using y to calculate x bar? Because that y refers to the y-axis. And it's always get confused when using these, so I think it makes more sense to call it x equals 0 to match the x that we have here. But if you're trying to follow this in the book, just be aware the book is using m sub y. And then for the y bar, it's almost the same thing, except we do the sum of the moments about y equals 0 divided by the total area. And notice the denominators are going to be the same. And y equals 0 is a horizontal line. So I'm trying to make a slice so that every point in that slice is the same distance from y equals 0. Would that be a horizontal or vertical line from the original region? Be horizontal. So for the y bar, I'm going to be taking horizontal pieces like this. So a moment, just like we had on that balance or on that scale, that balance scale, is going to be the distance times the weight. And I'm using area as a proxy for the weight because I adjusted the density, not have to worry about it. So first of all, I need the distance from y equals 0. And that is a vertical distance. Vertical distances are measured by y. And specifically what y measures is the vertical distance from the x-axis. So when I have distance from y equals 0, that's just y. It's for the area of this rectangle, I need base times the height. Let's see, the height of dx or dy? dy. And for the base of this rectangle, horizontal measurement or vertical measurement? Horizontal. What letter measures horizontal things? X. So what I'm going to have to do is get the x's for each side of this rectangle. Remember, the rectangle came from here. So for all the horizontal strips, what's the x value on the right side? So on the right side here, it is always 4. And on the left side it's always on this graph. So down here they're long, up here they're short. So for the left side, we have y is equal to x squared. But for us, we need the x equals root y. So this distance is 4 minus the square root of y. Huh? You are right. So what I said was everything on here has an x coordinate of 2. And that means that this right side is x equals 2, which is 2 minus 5. That's what I said, right? Thank you. Okay, so the area is going to be the base of this rectangle, which is a length of 2 minus root y, times the height, which is dy. And then it's that dy tells me I'm using horizontal strips, and it's each point along the y-axis that gives me one of the strips. What's the y value at the very bottom of this region? And the y value at the very top? 0. You have to evaluate these integrals? It depends. On the exam, no. On the homework, yes. And what do you do on the homework? Simbo Lab, Wolfram Alpha, your TI-80, whatever, TI Inspire. So any technology you need. So I'm more interested in you setting those up. I want to talk a little bit about horizontal strips. Horizontal strips are useful when you're uniform. So in other words, when you've got the right side and the right sides, all the right sides have one boundary, all the left sides have one boundary. And to use a horizontal strip is you need to be able to solve the original definition for x. You need x in terms of y. If that doesn't happen, then you can't use a horizontal strip. So that's this is going to be a bit different than what I have in my notes. Let's give an example. So y equals x minus x cubed. And the x bar is going to be easy to figure out. It's the y bar that's interesting. So we know the y bar is the sum of the moments about y equals 0 divided by the total area. And area is easy here. This graph starts at 0, 0, goes up for a while, and then at 1, 0, it's back. So the area is exactly an application of the very first problems that you solved with integrals. It was the sum from 0 to 1 of x minus x cubed. Thinking back to what we did here, it's our way of calculating y bar was getting the sum of the moments about y equals 0, which entailed us to draw a horizontal strip because everything here was the same distance from y equals 0. And then I had to solve for x to get the base. So if y is x minus x cubed, what's x? And see, that's a hard algebra problem. So if we tried to copy the method that we did there, yes, we've got an algebra problem that we don't even train you how to do anymore. So, at some point, before calculus was invented, did you know Harvard was a school before calculus was invented? So, at some point, right, is math people needed to do some sort of math. To keep the students busy, they teach them how to solve equations like this. But now we have more interesting math. So the last thing I need to show you is how to do the y bar with a vertical strip. And so here's the problem. Here is the y equals 0 line, just like we had here. Here is our strip. Remember, the way we do the calculation is we do the distance from y equals 0 times the area. The reason we chose a horizontal strip there because every point on the horizontal strip had the same distance. Here, though, is we have a bunch of different distances. That is the one problem we need to solve. This actually happened to Newton as well. So have you heard the story about the apple falling on Newton's head? Anyway, there's a famous story that is true even though it didn't happen. So the apple didn't really hit him on the head. The idea, the moral of the story is true. So what happened was Cambridge, Newton was 23, he was in graduate school. It's because of the plague, everybody was getting sick and dying, they closed school for a while. And Newton went back home to the family farm when he was 23, and he invented modern physics, so physics the way we do it now, our first approximation to how we do it now, and he invented calculus in order to do the physics that he had just invented. And his light bulb moment, or at least the way this is told, is he was sitting under the tree thinking. And well, as he was thinking about, I've got the Earth here and the moon here. And we know the moon goes around the Earth. And then when the apple fell on his head, he realized that the force that's drawing the apple to the ground is exactly the same force that's keeping the moon rotating around the Earth. Essentially, he invented gravity, he discovered, invented, I don't know how you want to call it, gravity. And he figured out that gravity is going to depend on two things. It's going to depend on how massive these are. The more massive they are, the greater the attraction. And it's going to depend on the distance in between. And here was the problem. Is when you're calculating the distance between the Earth and the moon, it really depends on which point you pick. So here's a point on the Earth, and there's a point on the moon. And there's a certain distance there. And here's a different point on the Earth, and a different point on the moon, and that's a different distance. How many distances does Newton have to worry about? Infinitely many. So do you guys have you had physics yet? Or enough physics to know the trick for this? What he did? He said it would be exactly the same gravitational force if we just concentrated the entire mass of the Earth into one point, the entire mass of the moon into another point. It's actually the centroid, by the way. And then, for the distance calculation, just do this one single distance. So the gravitational force measured with just this distance is going to be the same as all the distances that you would measure here. So we've got a similar problem for this example. We've got all these different distances. We've got infinitely many distances from y equals 0. And we're going to follow Newton. And we're going to collapse this whole mess into a point mass, into one just at the center. So if this distance is y, which is right there, if I collapsed it all to the center, how tall is that? So the middle would be at y over 2. So again, you're thinking about all these different distances, and when you have different distances, what you want to actually use is the average distance from y equals 0. So the average distance from y equals 0 is y over 2. And is this a dx or a dy? Dx. The area is going to be the base times the height. So the area is going to be y times dx. And you see the clash here. So I'm going to go clean up over there. You are going to fix the integrand. You're going to convert it all to x's. And then you're going to use this to put in the numerator up there. It's going to be an integral, and my y is given by x minus x cubed over 2. So I just took this y and replaced it by its definition, and y again is x minus x cubed dx. And that dx is telling me it's x values that give me an x. Each slice is determined by an x value, and those range of x values are 0. It's kind of amazing is not only do I get to have most of the fun, is I get to work out the problems and you just follow along, but they actually pay me for that. So I'm going to let you have the fun on this one. This is what I originally had in my notes. Oh, and by the way, this is my last example. So what are we going to do? We still have like half an hour into the class. We have almost, 2 hours left? Close to 2 hours, hour and a half. So what are we going to do for that extra hour and a half? Yeah, exactly. So what I'm going to do is I'm going to just talk about all the different types of problems you need to do for the exam. I'll work out 1 or 2 for myself. We'll just I'll show you quickly. I'll do a quick reminder how to do it. And then I'll give you a problem, and you'll try to do it yourself, and then we'll talk about what the solutions. Yeah, absolutely. Yeah, so if you're working on homework and your work questions, yeah, I'll talk about those. Oops. That's a better version. Let me show you the graphs. So the parabola is 4 minus x squared. The line is x plus 2. One of those intersection points is negative 2, 0. And another intersection point is 1, 3. The x-bar calculation should be straightforward. There's nothing new on this one. Is what I want you to practice is what we just talked about, how to do a y-bar calculation with a vertical straight. So you're going to work on that, and I am going to find some better pens. And when I come back, we'll do this together.